Alright, so we are at the last section of the chapter on quantum mechanics, and here we're going to bring everything together that we've learned in this chapter to explain what we see in the periodic table. The periodic table was discovered by Mendeleev, who discovered the existence of what we call the periodic law. And the periodic law is just the fact that when you arrange elements based on the order of increasing atomic mass, which is shown here, based on atomic number, what you see is that certain properties tend to repeat itself when the elements go back to the same group again. And in fact, that's sort of the basis of grouping elements. So for example, in this case, we're looking at atomic volume, and every time we hit the group 1A elements, lithium, sodium, potassium, rubidium, and cesium, those elements happen to have the largest volume compared to all the other elements in that same period. So if you look to period 2, for example, lithium would have the largest volume. If you look at period 3, sodium would have the largest volume, and so on. It was understood that there's some type of repeating pattern that occurs in the elements, and of course the idea is that there must be something about the way things are organized in the atoms of these elements that give rise to these periodic patterns. The first explanation we can give once we understand quantum mechanics is just the stability of the noble gases. So noble gases are elements that don't react with other substances. They're called inert substances. Some of the larger noble gases can actually react and form compounds with other elements, but definitely the smaller noble gases like helium, neon, and argon don't really react with others. The question is, why do they have such low reactivity? And it becomes immediately clear once you know how to write the electron configuration of noble gases that they are stable because they have filled the shell for the s and the p orbitals for that given period. So for example, if you look at helium, the only shell that it has is shell number 1, and the only orbital is 1s, and helium has both of the electrons in 1s, so it's completely full. If you look at neon, it's the second shell, or the second principal quantum number, and for that you can have both s and p orbitals, and both of those are filled completely. And if you look at argon, you can see that it also fills both the 3s and the 3p as well. Now, one of the things that people always wonder a little bit is that isn't there a 3d orbital in the third period? And the answer is yes, there is, but if you recall the way these orbitals are organized, the 3d is actually less stable compared to the 3p, right? So we sort of think of the s and the p orbitals as one type of orbital, and then the d is belonging to the next group of orbitals. It's not as stable as the p and s orbitals of that same shell. So that's the reason why when you look at the stability of noble gases, they only fill up the s and the p orbitals of that period, not so much the d and the f orbitals. As you'll see later on, one of the reasons that some of these larger noble gases can form compounds is because they do have those empty orbitals in that specific shells from the noble gas. The other thing that we can explain is the types of ions that form, particularly from the main groups. We had talked about how group 1A tends to form a +1 cations, and group 2A tends to form +2. And then when you get to the non-metal side, group 5A, 6A, and 7A tend to form -3, -2, and -1 anions respectively. Once we understand that the noble gases are extremely stable, it makes more sense how we can predict the formation of these ions. For something like a group 1A element, the valence electron happens to be in the s orbital, and it's only one valence electron. Because noble gases are so stable, the elements that are not noble gases would like to adopt the electron configuration of a noble gas, and they can do that by either gaining or losing electrons. For these elements here in group 1A and 2A, the easiest things for them to do to make themselves look like a noble gas is just to lose the electrons. So that's really how we can explain why certain ions are formed. If you go to the non-metal side of things, something like fluorine originally would have a configuration of 2s2, 2p5, and again you sort of look at what noble gas is closest to it. In this case it will be neon because helium is too far away, and for fluorine to make itself look like neon, the easiest way is to gain that one electron, and of course that's the fluorite ion. Now the next trend that we can explain is the trend in atomic radius. We're going to focus on the covalent radius first. So the trend, if you look at covalent radius, is shown right here. The group 1 elements has the largest radii when and you're looking at a given period. As you can see here, the size of the radii is increasing as we go down. So you can see that all these group 1 elements are increasing in size. Same thing with group 2, etc. And then if you go across that period, you can see that the group 1 is the largest atom. The way we can explain this is using that modified Bohr equation to calculate the energy of a given level or a given principal quantum number, where En is equal to negative RH times Z effective square over N squared. Z effective is the effective nuclear charge, which depends on the number of protons, the principal quantum number, and the angular momentum quantum number L. So when we go down a group, on a first approximation, the Z effective is constant. But remember that there is a way we can approximate Z effective. Z effective is equal to Z, which is the actual number of protons, minus the number of core electrons. So for example, for lithium, the Z is 3. There's 2 electrons that are in the 1s orbital, which is below the 2s orbital. That's the valence orbital, right? So if you take the two numbers, 3 minus 2, you get 1. So 1 is your Z effective. Again, this is an approximation. It's not the actual Z effective, but it's good enough to help us understand the trend. If you look at sodium, you can do the same calculation, but you also get a Z effective of 1. So in other words, the Z effective doesn't really change. In terms of your energy calculation, that means the numerator here is a constant. So then we have to look at the denominator, which is N. Remember, N is the principal quantum number of the valence electron, right? So that's shell number 2. For sodium, it's shell number 3. Now, what's the effect of moving from one period to another period in the energy calculation? I'm actually showing it right here. Your E sub N for lithium would be negative RH 1 over 2 squared, or 1/4 of RH, whereas for sodium, it would be 1 over 3 squared, or 1/9 of RH. What we just said is that the energy that is holding the valence electron for lithium is going to be stronger because it's a bigger negative number compared to the energy that is holding the valence electron in sodium. If it's harder to remove the valence electron, that must also mean that the valence electron is located closer to the nucleus. So that means lithium atom must be a smaller atom compared to the sodium atom. Now, what about when you go across the period? We say that the largest atom is on group 1 and then just progressively becomes smaller. Similarly, you're going to look at that equation and try to explain based on the size of the Z effective as well as the N. Now, what doesn't change when you go from left to right? The N in this case doesn't change because you're in the same period. All the valence electrons are located on the same shell. So the N is constant. The Z effective, on the other hand, increases because the Z itself increases. The actual number of protons increases. And so if you calculate the Z effective using that rough approximation by taking the number of protons minus the number of core electrons, you can see that the number of Z effective for lithium is 1, as we did earlier, but for beryllium it's going to be 2 because beryllium has 4 protons, but the number of core electrons doesn't change. And as you go from left to right, the Z effective gets bigger and bigger, so the energy gets stronger and stronger, meaning that it's harder to remove that valence electron from fluorine compared to from lithium. If that's the case, that must mean that fluorine has a smaller size because that valence electron is closer effectively to the proton or to the nucleus. Okay. Now, what about ionic radius? So whether atoms lose or gain electrons is going to change their sizes. If cations are formed, they're going to be smaller than the atoms because their Z effective is higher in the cation compared to the atom. In the atom, you have repulsion from that extra electron, but if you remove that electron, then the repulsion is less. If the repulsion is less, then if your nuclear charge is higher, effectively what we're saying is that your valence electron is closer to your nucleus, so the cations are smaller. Anions is the opposite. You're gaining an electron, so you're generating extra electron-electron repulsion because of the extra shielding. Now that's going to lower your Z effective. You're going to get a bigger species, larger than the atoms that they come from. You can actually see this. The gray color sphere in all the pictures is the atom itself, and then the red color spheres are cations, and then the blue color spheres are the anions. When I compare cations to their atom, the cations are always smaller, but when you compare anions to the anions are always larger. Now we have something called the isoelectronic set of ions, which just means ions with the same number of electrons. The word iso means the same. If they have the same number of electrons, that means all that matters is just the Z, or the number of protons in each of those ions. So for example, here's a series of isoelectronic ions. Oxide chloride, O2 minus, fluoride, F minus, sodium plus, magnesium 2 plus, and aluminum 3 plus. They all have 10 electrons. The amount of repulsion is the same in all of these species. However, the nuclear charge is different. In oxygen, we have 8 protons. Fluoride, we have 9 protons. Sodium ion, we have 11 protons, and 12 protons for magnesium, and then 13 protons for aluminum. Because number of protons increases, the sizes get smaller because they have the same number of electrons that are being attracted by a larger and larger nuclear charge. You can see this gets smaller because there's the actual number right there. In picometers, this would be 140 and 133 picometers. So the fluoride is a little bit smaller, but then sodium ion is 97 picometer, which is smaller than 133, right? And then 66 for magnesium and 51 for aluminum. Now that we look at the trend in atomic and ionic radii, we can really apply the same concept that we discussed here to many other properties that we can observe for elements in the periodic table. First one we're going to look at is trend in ionization energy. So ionization energy, or I, is the amount of energy that you need to remove one electron from a gaseous atom or ion. The electron that you're going to take out, of course, is the valence electron, because the valence electron is further away from the nucleus. You can actually measure the ionization energy using an experiment called photoelectron spectroscopy, or PES. So this is actually data that's shown for a PES experiment. In a couple of prior videos, I had used one of these data to actually calculate the effective nuclear charge for a given element. So the first thing to look at is just that ionization energy increases as you remove more electrons. So here's an example for magnesium. When you remove the first electron from magnesium, I1, or the first ionization energy, is 738 kilojoules per mole. So that's an endothermic process. When you remove the second electron, the ionization energy jumps to 1451 kilojoules. And of course, this makes sense because the number of electron-electron repulsion has dropped by 1, going from magnesium to magnesium plus. However, the number of protons stays the same. You still have 12 protons there. As a result, Z effective is higher for magnesium plus, which of course means that it's going to be more difficult to remove the electron from magnesium plus, and that's what we see here in the data for ionization energy. Now here's the actual trend for ionization energy. The ionization energy for noble gases are the highest, and that makes sense because they are the most stable of elements, right? So it's really hard to take away their electron. The ionization energy for the group 1 elements are the lowest in that same period. So within the period, you can see that the ionization energy increases. That shouldn't be hard to explain because, as we said earlier, the strength of attraction between the valence electron and the protons in the nucleus gets stronger as you go from left to right in a period. So that would make sense why the ionization energy now increases, because it should be harder to remove valence electron from a smaller atom like this compared to a larger atom. Vice versa, we would expect ionization energy to decrease as you go from top to bottom in a group because the size of these atoms get bigger, so the valence electron is located further away from the nucleus, so there's more shielding and it should be easier to remove. In fact, when we look at the actual patterns here, we can see that lithium has a higher ionization energy compared to sodium. Sodium has a higher one compared to potassium. Potassium has a higher one compared to rubidium, and so on. So one of the things that I want to talk about is not just the trend, but also these jagged lines here, which must have meant that there's an exception, because what we expect is there should just be a straight line here going from lithium to neon. So what this is saying is that when we go to that element and then we go to the next element, the ionization energy drops instead of increases, even though we're going across a period. So we can actually see it for magnesium and aluminum. So you can see that the energy of magnesium is 737, but then for aluminum, instead of going up, it actually drops down to 577. So why is that going on? The way you answer these type of exceptions is always to look at the details of the electron configuration, because to explain the trend is to look at the Z effective and then the principal quantum number. So if we have an exception, that must have meant that there's something more small scale that is going on that we need to look at, and the only way to find that out is by looking at the electron configuration of the two elements themselves. So here's magnesium, which is Ne3s2, and here's aluminum, which is Ne3s2 3p1. Now the question is, why is it easier to remove the valence electron in aluminum compared to magnesium. Well, what's the difference in the two? 3s will be the orbital where you're going to pull the electron from if you're trying to remove the electron from magnesium. But for aluminum, you have a choice of either 3s or 3p. Now, of course, in nature, you're going to do something that requires the least amount of energy, which in this case means you're going to remove it from the 3p because the 3p orbital is less stable than the 3s. Now, in fact, that's exactly the reason why the energy is lower. Once you go to the next element, which is silicon, that pattern should come back up because now you have 3p2, which means that you're removing 3p compared to another 3p. So that there's no special reason there why that trend would not continue again. And there's another change here for another element. You can see that in the plot itself, there's another jagged drop here. And so that has to do with the transition from phosphorus to sulfur, which goes from 1000 to 999. So again, there's a drop in ionization energy when we expect an increase across. Here again, I'm going to look at the electron configuration of phosphorus versus sulfur. They both have 3s and 3p orbitals where their valence electrons are located. With phosphorus, you have the 3 electrons. With sulfur, you have the 4 electrons in the 3p orbital, which of course means that one of those electrons is paired up. Now, as we know, given Hund's rule, the pairing of electrons we try to avoid because pairing increases electron-electron repulsion, and that in fact is the reason why the ionization energy for that specific electron in sulfur is less compared to the one in phosphorus because there's already electron-electron repulsion for that electron, so the removal of that electron takes less energy. And again, the difference between these two numbers is not that big because that effect is fairly small. When you're going through this chapter, think about explaining both the trend as well as the exception that we observe here. Let's take a look at one more property that shows a trend, which is electron affinity. This is the energy that you observe when you're adding an electron to a species. That species could be an atom or an ion in a gas phase. So for example, for fluorine, when an electron is added to make a fluoride ion is negative 328 kilojoules per mole. So that's the first electron affinity for fluorine. For ionization energy, the value is always positive because it always takes energy to remove an electron. But for electron affinity, it could sometimes be exothermic, could sometimes be endothermic. It just depends on who you're adding the electrons to. So you can see here in this table of electron affinity values, most of them are negative, but you can see that for nitrogen, for example, it's a positive. Nitrogen is similar to phosphorus in terms of its configuration, so it has these 3 electrons already, and you're adding one more, and that one more has to be added to one of the already occupied orbitals, which means you're going to generate repulsion that doesn't exist before. And when you do that, you cause the system to be less stable, so adding electron actually is not tolerated. But then once you do that one time, then the system is a different system at that point. Then from then on, when you measure relative to that new system, the addition of the electron is more tolerated. Now, you might say like, well, why doesn't that happen with oxygen? And oxygen is different than nitrogen because in oxygen, you add one more proton to it. So the addition of that one more proton and the smaller size of oxygen causes the addition of the electron to be more tolerated because there's stronger attraction with the nucleus. One more trend to look at is something called transient magnetic property. Remember that electrons spin, it generates this magnetic field. And so there's 2 types of magnetic properties that we can think of. In a diamagnetic atom or ion, all the electrons are paired. Okay, so you don't have any single electrons. So the spins of the electrons cancel each other, so you don't get magnetic properties. These diamagnetic species is only weakly repelled by a magnetic field. A paramagnetic atom or ion, on the other hand, has a bunch of these single electrons, and because those single electrons have their own spin, it's not canceled by the opposing electron, they have pretty strong magnetic effect. So if you put a magnet next to one of these type of species, you're going to get a strong magnetic attraction. Okay, a lot of times what we would ask is this species diamagnetic or paramagnetic? And all you need to do is really just look at the electron configuration and see whether they have paired electrons, all of them, or they have some single electrons. We talked about atomic radii, we talked about ionization energy, we talked about electron affinity as well. With electron affinity, we tend to see more exothermic value as we go from left to right, and as we go from top to bottom, we see less and less exothermic value. And then we didn't talk about metallic or non-metallic character, but the reason why things become more non-metallic because non-metals tend to accept electrons more easily, and that trend goes along with the electron affinity trend. With metallic character, the more metallic you are, the more likely you are to lose electrons, form cations, and of course ionization energy decreases as you go down, making it easier to form cations. So as a result, the elements that are down here are more metallic metallic than the elements that are up here. Now, one of the useful things about these trends is you can help explain chemical reactivity, which is really what we want to be able to do eventually. For example, we can think a little bit about the reducing power of a group 1a elements in this case. When you put a reaction between a group 1a element like sodium or lithium with water, you have a very explosive reaction, and the reaction is actually a redox reaction. This is what a typical reaction would look like. So this M here is any group 1a element, could be lithium, sodium, potassium, etc. Now, as you go down that group 1 elements, the reaction becomes more and more explosive. It generates more and more energy. And so the question is, why is that going on? If you look at this reaction carefully, a reaction is basically a conversion of the atomic form of the element into the cation form of the element. So you're losing an electron in this case. Why is it easier to lose that electron? Because the reaction generates more and more energy. That means that the process becomes more favorable as you go down the group. Well, the reason is because the ionization energy actually decreases from top to bottom. That means it gets easier to remove the valence electron. Then the reaction happens more easily and generates more energy as it occurs.